Welcome back to the OWASP Top 10 Explained tutorial series, and what we are doing over the course of 10 videos is to look at the OWASP Top 10 most serious web application vulnerabilities as detailed in their 2013 list. And a new list is coming out soon, I think in the next month or two. But most of these will probably stay in the top 10. I'm not sure if there will be any new ones. Their order might change, but in some ways I think we still need to understand all of them and help us as professionals, as software developers and engineers, to see a bigger picture when it comes to web application security. Now, one thing I haven't mentioned before, I don't think, is that I highly recommend that you download a copy of the PDF that contains the OWASP Top 10, because in some ways it's probably useful for you to read it in conjunction with this video, just because there will be a few things that I probably won't cover. There's obviously a lot of detail in some of these issues, and I simply don't have the time to go into it in great detail at the risk of creating a very long and possibly boring video. So anyway, let's crack on with this. A6 is called sensitive data exposure. And what we're talking about here is quite simply that some data that web applications hold, and in fact possibly most web applications hold, have high value. Now there's obvious ones like credit card numbers, like email addresses, other personal data, so health information, private information, things that perhaps you don't want people to know about yourself. But also things like passwords have value, even if it's just to give an attacker access to a different system, a different web application, where they are going to assume that you've used the same password. So clearly, if this data is not correctly handled by your application, then data exposure is a serious risk, and therefore that makes it a more likely outcome. And none of us want to be in that place in the news where it's our web application that's being compromised, especially if the security controls that we were using were really not very good, not very suitable for the job, because then that makes us look like we don't really know what we're doing, and that's going to have all sorts of knock-on effects, both personally and on our business as well. So how common is sensitive data exposure? Well, there's two things really that we need to understand here. The first is that it is possible to implement insecure security controls on the data, but yet not expose that, because we have other good controls in place in our web applications. But clearly, the more chance that we have of storing data in a kind of an unprotected way, the more likely it is that a certain attack vector one day is going to allow an attacker to get access to those credit card numbers, that health information, whatever it is. And evidence, certainly my experience, suggests that very few applications, web applications, have a pessimistic encryption policy. In other words, most people store things in plain text by default, and probably most of them will store passwords using a hashing algorithm, especially if the framework does that for you. And other than that, very few people will encrypt data unless they have to, or unless they have a good security mindset, a good security culture in their company. But even if encryption is applied, it might be applied at the wrong level. So for instance, if you were to encrypt the database hard disk or the database server's hard disk, but the data itself is not encrypted, then the web application still has access to plain text data, and any vulnerabilities in the web application have access to the unprotected data. What the hard disk encryption would do would be to protect you from, say, having hard disks stolen or having hardware stolen from your company, but it wouldn't prevent vulnerabilities in a web application from exposing that data. So some sites are even found not to apply PCI DSS requirements for credit card storage. So if you handle any kind of credit card data, the industry has a body, and the data security standard is the document they produce. And the payment card industry require that anybody handling credit card numbers has to abide by the data security standard and effectively either be audited or self-certify that they meet all of the requirements. But yet people are still being caught out. Sometimes quite large retailers are being caught out where they're doing things that they're simply not supposed to do. And sadly, the PCI don't ever seem to take any serious action against those people other than telling them not to do it again. They might well put up their charges for using the credit cards, may or may not make a difference, but you know, people are still not doing it right, even when there is a framework for them to use. But what should be mentioned, as I said earlier, is that just because something is insecurely stored doesn't mean that it's easy to attack. Attacking weak cryptography, which is the security control that we use to protect our data, in itself is usually a very hard thing to do. And if we look at things like some of the theoretical attacks on SSL and those sorts of things, sometimes you're talking about massive amounts of data that need to be produced in order to actually take advantage of these vulnerabilities. Even if an attacker manages to get hold of a list of database password hashes, then if it's done, you know, even semi-properly, there's still quite a hard amount of work for the attacker to do to actually make use of those things. So although the poorly secured data is quite common, being able to attack it is usually quite difficult, and therefore that's why this issue is at number 6 and no higher. But of course it kind of goes without saying that the outcome for data exposure can be very severe. And there have been a few cases recently where a healthcare provider got hacked and people's personal health data, I think it was in the USA, people's personal health data was stolen. And okay, for some people, maybe they don't really care too much. But of course, for some people who have very severe and perhaps embarrassing health issues, they certainly don't want that information to be publicly available. And of course, they can then become the target for unscrupulous salespeople trying to sell them health products and things like that. And there's a whole raft of other serious outcomes from having data exposed. So despite the fact that it might be hard to exploit, the outcome can be very severe. So we still need to take it seriously. So here's one example, and I found it quite interesting for a number of reasons, but back in 2013 there was a vast breach of an Adobe server, and I think it was 3 million user accounts were stolen, as well as a lot of files and stuff on various hard disks and things. And here's an example of the 5 columns of data that were obtained by the attacker. So they had a user ID, which is kind of common, that's a number. They then had a password, but rather than being hashed, it was encrypted. Now, normally that would be an alarm bell, because encrypting data means it can be decrypted. And that in itself is quite worrying, because you don't need to decrypt passwords, you just need to be able to check them, and that's why the best practice is to use hashing. Anyway, they used encryption. Not only did they use an old algorithm, triple DES, which is not really kind of recommended anymore. It's a little bit old, a bit long in the tooth, has quite a short effective key length, but it also used this electronic code block mode. And what that means is a block of data is encrypted at a time, and those blocks all get joined together. And significantly, that means if you encrypt the same password twice, you will get the same value. And that is not a desirable feature of encryption, because what it means is you can use the information in one person's in the row for one user to actually tell you what someone else's password is. Significantly, when you use some different chaining modes like cipher block chaining and some of the counter modes, you can pass in what's called an initialization vector, and what that does is it adds some random data so that which then feeds into all of the different blocks as it goes along, which means that you can then encrypt the same password lots of times and get a different answer. So then you lose the ability for the attacker to cross-reference passwords. But in the case of Adobe, they didn't have an IV. What they had was data that looked like it was secure because you couldn't read it, but it was done in a poor way. But then significantly, they had a password hint which was stored in plain text. Surprise, surprise, a username in plain text, an email address in plain text. So even ignoring the passwords here, you've already got an awful lot of information which the attacker had to do no extra work for. But the interesting thing about this particular breach was it permitted a side channel attack. So to attack encryption, you would usually imagine that you either have to find the key or you have to crack the encryption itself, either using some kind of mathematical attack or brute forcing all of the keys or something like that. But if you think about this case, these are just obviously fake examples, but imagine user 123 has a password which when encrypted, it kind of, ABC 1 2 3 4 5 6, that doesn't mean anything because the data's encrypted. But imagine that user 123 has put in a password hint of password is password, and these were real examples of hints. People put numbers 1 to 8, the usual password, open sesame. Some of them put the password in the hint, and of course the hint is readable because it's in plain text. So guess what then, when I look at user 321 and I notice that their password is also encrypted as ABC 1 2 3 4 5 6, guess what? I can now deduce that this user's password is also password, because I know that the encryption will always do the same thing every time. So as one website kind of joked about, what you ended up with was the largest kind of crossword puzzle ever, because once you solved all of these different password hints, you could apply the information to everyone else who had an identical encrypted password. So this was kind of wrong in lots of ways, but it demonstrates again people using a poor choice of encryption and people putting stuff in plain text when in most cases there's no need to do that. So how do we fix it? We're talking really here about how do we use encryption to keep our data secure. Well, one of the first things that we need to do is we need to take what I call a considered view as to the value of your data. Now, if you're a small company and you only have 1 or 2 web applications, then you might say, well, let's just assume that most of our data is valuable. We'll assume that email addresses are valuable, passwords are definitely valuable, any kind of things to do with private data, healthcare, religion, sexuality, all those sorts of things, we'll assume that they're high value data. But of course, in a larger company, you can't actually do that because you probably have so much data that at some point you've got to consider what data is worth the most and needs to be protected first, and what other data can we live with it being exposed, if in the unlikely event of somebody breaking into our system, they're able to see that data. So we need to take a view. We need to spend more effort protecting our more valuable data and our more valuable systems, right up the stack, not just the data itself. But in this case, we're talking about the encrypted data. Another thing that's really, really important is learn about encryption, all the different sorts of encryption. So I've interviewed a number of software developers over the past few months, and I've found that developers' understanding and knowledge of security is woefully poor. You ask somebody, why would you use AES instead of DES, and most people wouldn't even know, or they'd have a guess. Or why do we hash passwords rather than using symmetrical encryption? Why do we use symmetrical encryption instead of public key encryption in most cases? All of these kinds of things, they're kind of fundamentals really, I think, for any web developer. Even if your job is not primarily security, I think it's important that you understand these things, because then you are another pair of eyes on the systems that you're producing to spot things that get missed and say, hang on a sec, I'm pretty sure this should be encrypted, or I'm pretty sure we haven't set up the encryption properly. So learn about it. There's not a great deal to learn at a top level. You can go into it in detail, but in some ways you don't really need to. But learning the top level concepts, why they are like they are, what they do, is really important. Another thing is that symmetrical encryption particularly is generally very lightweight. It doesn't take a lot of CPU. It's not going to kill your server. So I would suggest that you should apply encryption as your default position and only choose to not encrypt it if there's a reason not to encrypt it. So for instance, on one of my database tables, there's a certain column that I can't encrypt because I use it to look up a row in the database table, and because encryption will always produce a different value with the IV that we talked about earlier, then I can't use symmetrical encryption for that data. In that case, I use a hashing algorithm because a hash is consistent when symmetrical encryption is designed not to be consistent. So when you understand about encryption, about the different mechanisms, you can then choose how you're going to apply it. But, try and consider using it as your default position. Learn how your framework encrypts data. Learn about keys. How do I generate keys securely? How do I, encrypt this stuff in a suitable way? And also, we'll look at in the next slide briefly, is you need to consider the different levels in your application, because there isn't just one kind of encryption at one level. We talked earlier about full disk encryption or hard disk encryption, but there's encryption of data, there's encryption of transport layers, there is hashing types of encryption. There's all these different sorts, different applications, and we need to look at encryption at different levels and try and be as formal as we can and say, right, what is the risk that we're trying to protect from? So we can encrypt data, and then maybe our hard disk gets stolen, or maybe the person who's supposed to destroy it loses it somewhere, and we need to be able to ask those questions. Say, right, what would happen? Would that be okay because the data's encrypted, or would they still get information that means we should really encrypt the hard disk, even if that costs us extra money and takes us more time, and if it makes the system a bit slower? Software development, software engineering is a question of balance and trade-offs. Do I trade off speed for security? Do I trade off maintainability for speed? All of these different things are important, but security is not something we can carry on ignoring. Another fairly important concept, and it might seem obvious, but it's not always obvious when you're trying to do it yourself, is not to store encryption keys in the same place as the data it is encrypting. So a good example of that is we will often encrypt data and put it into a database. But then somebody might think, oh, let's create a table to store our encryption keys in the database. Now, at one level that makes sense because it just means everything's in one place. I can store the keys, I can back up that data, I can restore it again on another machine, all of the stuff's there and it's all going to work. But of course, clearly the danger there is if the database gets stolen, then somebody gets the keys with the data. That's a bit like leaving the keys to your safe on the top of the safe. So when it gets stolen, the attacker has the keys and they can get in. So you need to think about where your keys are stored, how they're secured. You can put them on disk, but does an attacker might get access to your disk. Is there something else you can do? Is there a way to store them in a hardware security module? So there's lots of kind of things around that you can learn about, which kind of leads us on to this last point here really. Use hardware protection for the keys wherever possible. So the way that hardware security module works is the key is generated and stored within the module. So there is no physical way to take that key off of the device. And then when you need to encrypt data, you send it to the module and it decrypts it or encrypts it, whatever you want to do. But the important thing is, if somebody tried to steal the data off of your disk, they would physically be unable to steal the keys. And even if they physically tried to remove the device, some of them have tamper detection and can, destroy the keys and stuff like that. So there are kind of different hardware protections, including ones built into normal servers as well, using something called trusted platform modules. So I talked earlier about the different sorts of encryption. So again, we've got encryption at hard disk level. So that just says everything that gets written to the disk is encrypted. The keys are stored in the trusted platform module, and usually they require some kind of password on boot up. Now, it's a bit weird that BitLocker on Windows does not require a password, so it's kind of a bit worrying because it makes me think that the key to unlock it would be available to an attacker because it's available to the operating system on boot up. So I don't quite know how that works, whereas TrueCrypt used to require a password, and that password formed part of the key to decrypt the hard disk. So that's pretty useful. It's useful for protecting against data theft and equipment theft. But then when we move into the kind of more software application level, we can obviously encrypt data at rest. We can use symmetrical encryption if we need to decrypt it. We can use hashing, but we need to use the right sort of hashing. I don't really want to spend a lot of time on this because this could be a whole video in itself, and I might do that maybe at a later date. But basically we need to use cryptographically secure hashing, preferably a slow key stretching type algorithm. So we're talking bcrypt, scrypt, pbkdf2, or more recently something called argon2 is the latest one of those, and they're all designed to be slow, which means that if an attacker does get the data and is trying to brute force those hashes, it takes a lot of time. So a lot of time to an attacker might be half a second, which doesn't sound like very much, but if you have, you know, a billion combinations to attempt, then clearly if each of those takes half a second, then that's not going to happen. So you need to use the right sort of hashing. We have transport layer security. So here we're mostly talking about links between browser and web application, but we could be talking about load balancer to web server. We could be talking about web server to web service. We could be talking about web application to database. So any kind of link that is using TCP/IP and going across the transport layer, in most cases should use TLS, but that needs to be configured correctly. We then got public key encryption. It's used for a number of different things. We use it for the initial key setup in HTTPS before symmetrical encryption takes over, and that's because symmetrical encryption is faster than public key encryption. Public key encryption is used on things like PGP, email services, other services as well. If you have any kind of system that needs to send something securely without being able to perform a key exchange, then this is basically the boy to do it. We then have any kind of inter-app communication links which we need to consider for encryption, and again some of them might be able to use TLS, but others might be special. They might be RPC, they might be SOAP, they might be various things which may or may not support TLS directly, might have their own security mechanisms which include cryptography. Database connections, again, might be able to use TLS, might not, might have their own mechanism. But even encrypting things like the configuration. So if you have a database connection string in a configuration file, how do you protect that? Because if somebody gained access to your disk, is it a simple job of opening a file and then they can access your entire system? Or do you have extra measures in place to actually encrypt that configuration or obscure it in some way that makes it much more difficult for an attacker to gain that information? And one of the ways of kind of analyzing these things is to use something called STRIDE. There are other ones that you can use, but STRIDE is quite a useful one. It stands for spoofing, tampering, repudiation, which means denying that you did something, information disclosure, denial of service, and elevation of privilege. So when you've got all of any kind of link between two different entities, you can perform a STRIDE analysis and say, right, could this link be spoofed? Could it be tampered with in a way that would give the attacker some kind of advantage? Could a user or a third party claim that they didn't carry out an operation that they did? Is it possible for any information to be disclosed accidentally by this link? Could it be used for denial of service? Could it be used to elevate privileges in some way? So all of these questions can be asked of all the different links. In many cases, TLS will stamp on most of them, but you might not be able to use TLS, and you can still kind of ask these questions. And so I want to finish really just with one example. Microsoft create a great threat modeling tool. It's based on Visio. If you've ever used Visio, it's kind of a similar drawing experience. And how it works basically is you draw boxes to represent your different systems. You draw boundaries which separate your systems. So you might have a web application as a box. You then have a boundary which then has a browser the other side of the boundary to show that there is a trust difference between your web server and the browser. You might also then say, well, I've got a database server and maybe there's another trust boundary. And then you just draw lines between all of the boxes where they link up. And then the tool itself will automatically generate you a stride entry, an S, a T, an R, an I, a D, and an E for each one of those links, where you get to think of every single element of every single link and say, right, how do I protect against DOS on this link? How do I protect against this? How do I protect against this? And obviously you can put in saying something like, we use TLS, and that fixes it. Or we might say, we can't apply any controls, but this is an internal link and we think it's suitably low risk. But that's up to you. The point is that you've thought about it. And then what you can do from that, once you've filled it all in, is you can generate a document which then becomes quite a nice little threat modeling document which shows that you've considered the different parts of the security. So if you search for SDL threat modeling tool, you will find it. There's a link there anyway. And there's lots more we can talk about with sensitive data. I guess the headline items are, first of all, consider the value of the data that you have. It's probably worth more than you think. The second headline is learn about encryption. The third headline is make sure that you do encryption in the correct way to suit the data that you've got. And then, like with all of these things, have your code review checklists. Have your your monthly review where you're looking back at it and saying, is this still correct? Do we need to reconfigure it? Do we need to switch off SSL version 3, or is there a TLS 1.4? Whatever those things are, get your software process in place. Make sure these things are plugged in somehow, and then hopefully you will avoid being another Adobe. So thanks for listening again. Again, questions or comments, please put them below. And I will try and do the next video fairly soon.